So I will speak about generalization of Hall's theorem. So Hall's theorem, Hall's marriage theorem, says that if a graph has good expansion properties, then we can use it to solve matching problem. But for applications, people want a dynamic variant of matching problem, and so we will give a variant extension of Hall's theorem that allows for dynamic matching. Okay, so let's start. The overview of the talk. So you can go to next slide. So I will first explain what is the problem. I will say what is original Hall theorem. I explain the main result, and then I will give application to constant depth non-blocking networks. So by the way, expander graphs were first introduced by people who studied something called switching networks, where you need to send information through a network where the edges have certain capacity, and you need to connect various inputs to various outputs. Okay, and that will be the first application. Then if I will see how much is time, I can tell about the proof, and then I will speak about a second application in the very end. And the second application uses a variant of the result. So it's an incomparable result. And so we improve constructions of a data structure that saves a certain set and can answer questions like, does this element belong to the set, yes or no? So that's the plan. So the last part is just 10 minutes, it's short part. Okay, and the proof will depend on the remaining time. So let us go to the problem. Next slide. Matching is a set of disjoint edges in a graph, and we will always use bipartite graphs here. And so here we said that this graph has offline matching up to 2 elements. And what does it mean? For every choice of 2 elements at the right, we can find 2 edges that covers these elements at the right and are disjoint. So in the next slide, you see an example. So if we take the bottom 2 points, we can find the next slide, these edges cover the nodes and are disjoint. And similar for top, all possibilities of 2 points at the right, we can cover by disjoint edges. Okay, so now next slide is about what's the dynamic matching game. So there are 2 players. Our adversary, what he does is he removes edges from the matching. So he doesn't change, the graph is always the same, but just he removes the edges from the selected edges. And afterwards, at most, we can have k-1 edges. And then he will select a right node, and we need to select a left neighbor for it. Such that the corresponding edge is, so we have to add an edge that covers the selected right node, and it should again be disjoint from the other edges. And if we cannot do this, then we lose. And so we say that a graph has dynamic matching up to k elements if we have a winning strategy in this game. So there is an example. So let us first see that this graph does not have dynamic matching up to 2 elements. So what does the opponent? He selects the node in the middle, and then we can select any edge, you can show it, and then opponent can select the top node. And so we cannot add an edge because the edges have a common endpoint at the left. So this graph does not have dynamic matching up to 2, but it has offline matching up to 2. Okay, so go to the next slide. That's fully connected bipartite graph, and this has dynamic matching up to 2 elements, and that's quite obvious. Okay, so let's remove 1 edge in the next slide, and then this graph does not have dynamic matching up to 2 elements. So now is the question, can you tell what the opponent should do.
Bruno, it's not clear. What do you mean when you say that the opponent removes edges? How many edges he can remove from the graph?
And any number of edges.
For example, all the edges.
Yeah.
But then it's clear. The opponent just removes all the edges and there is no matching at all.
No, but he doesn't modify the graph. So the match, he removes edges from the matching, and the matching is a subset of edges.
Ah, he removes edges which are already in the matching.
Yeah. So the graph remains the same.
Okay.
Never changes. Just the set of edges is modified.
So the two upper nodes are identical, so it doesn't matter which of them the opponent chooses, I guess. So he chooses one of those, right?
Yeah. Okay, in the next slide, I chose the bottom one. And so now opponent can choose a neighbor. Again, there is symmetry. No, there is no symmetry. Yes, and now imagine we choose this edge.
There is no symmetry, so you need to choose the middle node.
But okay, if you are an opponent, I need to choose an edge, and I choose the top one.
Okay.
So now, what do you choose? Sorry, Maxim, I'm playing the game with Nikolai. So go 2 slides back.
But you see, the player wins, right? So you said that.
So the game continues indefinitely. It's a dynamic matching game.
Indefinitely.
Yeah. Okay. So Artyom, Kolya selected the middle node. Then I choose the upper edge. So go to the next slide. And now I'm waiting for somebody to tell what opponents should do to make us lose. So there are 2 choices for the next node. Okay, you can also remove the edge, but that doesn't help. I mean, you can always postpone removing edges. It can only help.
So probably the bottom node.
Yeah, I think that would be a good plan. But okay, so now let us think the bottom node. Let us think what happens. Can you go 1 slide back?
This is the upper node.
Yeah, I choose another strategy in the slide, but it doesn't matter. Let us think that we choose the bottom node. I will make some annotations now. Don't change the slide. Annotate. And so let us think that we choose this slide. What's this? So let us pretend that we have this node. Then there is only one edge, so we must select this node. And indeed, now we can win, because in the next move, we can remove this edge. And so now there are at most 1 edge left, and we can select this node. And now, oh, no, it's not working.
So it's not clear. I mean, the rules of the game are not clear. So in which case the opponent may remove an edge.
He can if it's his turn, he can remove any number of edges, but the graphs remain the same. The matching is a subset of edges, and this subset can be modified. So we have to add edges, and the opponent can remove edges.
So he removes an edge from the matching, which means that the matching is not good now because he has removed it. So and when he removes a node from the an edge from the matching, does it mean that he also removes the upper end of that edge?
So the game is played on a graph And what is modified is the matching. So together, the two players modify the matching.
Ah, I see. I see.
And the adversary also selects the right node.
So the adversary selects the right node. I mean, the opponent selects the right node. Then we select an edge incident to that node. And then the opponent can also remove some edges.
Yeah, an old edge, and then select a new node.
And we win if we can play indefinitely long.
Exactly, yeah.
So, and you claim that here the opponent wins.
Yeah.
It's not clear how he wins. So he selects first, he selects the middle node, right?
Yeah, that's correct.
So assume that we have selected this edge, then each node selects the opponent.
The top node, it's in the next slide.
The top node.
So then we have only one choice, which is the bottom node.
Yes, right.
Now we remove the edge from left top to right middle.
Okay. And then the opponent selects the
the bottom node.
The bottom node. I see now.
Okay, and we have to check two replies because when the we should also think when the first of our move was going to the bottom instead of the top left node.
Right.
But okay, I didn't make a slide for this. Okay, so this is of course a very important point. That's the definition of the game. So we need to be sure everyone understands it.
So does anybody have questions about the definition of the game? So you see no questions. That means that everybody understands it.
Okay.
Especially Marius, I guess.
Yeah. Okay, then let's go to the next slide. So what we have to do, our task is to given two numbers n and k to make a graph with n left nodes. Sorry, with n right nodes. There are, and in the paper the order is flipped. So n right nodes, and that wins in which we can win the matching game up to k. And so there are quite some applications for this problem. And there are different criteria. And what do they want? Is that the graph has few edges. Then the right size, the left size should be close to k. So the lower bound, we cannot have matching up to k if the left set is fewer of k nodes. So k is an upper bound. And we want our graph to have left size close to k, not too much. Also, the matching strategy should be fast, and we want to build our graph also fast. And so what means fast? Fast means polynomial in log of n. N is the right size. So we will have n typically much bigger than k. But if n is equal to k, it's very easy to build optimal graph, just for k n horizontal edges.
But say it again, what about the number of the right nodes? Do we choose that number?
No, it's given. So number of right nodes is n. It's large and it's given.
No, wait. You have written that n is the number of left nodes, right?
Yeah, it's a mistake on the top line of the slide. It must be a right size. Sorry for this.
Okay.
Yeah. And left side, it should be close to k. We want a fast dynamic algorithm, a fast way to build the graph. And so our main result is that we can build such graphs in which the first three criteria are optimal up to a factor polynomial in log n. So that means number of edges equal theoretical lower bound. Lower bound is at least k, and we can get number of n times the lower obvious lower bound is n, number of right nodes for the and so our graph will have edges n times polynomial and log n. Sorry, I'm not right. The low.
So you mean the total number of edges, or
yeah, total number of edges. So the optimal is
not the degree. So you don't care about degree, right?
Well, yeah. So they will be right regular. So all the right nodes have the same degree.
And when you say about lower bound, you mean there is such a lower bound even for.
Yeah, there is trivial lower bounds. If we have n right nodes, we need at least n edges.
All right.
Because we cannot have 0 degree.
You said that up to log n factor. Okay.
Yeah, we are optimal for number of edges. Then for the left side, trivial lower bound is k, and we can get k times polynomial in log n. And matching time is also polynomial in log n. So trivial lower bound is 1. So all three are optimal simultaneously polylog n. And now if we want it with explicit graph, then we have a little bit, we have all 4 criteria simultaneously optimal, but that's quasi-polylog n. Actually, the 4th one is also optimal. So the building, so given a right node and some index of the neighbor, we can compute the left neighbor in time polylog n. So it's slightly bigger than what is given here. Okay, so these are the main results, and it has some applications, I think, in the next slide. Oh, wait. Sorry, go to the next slide. And so how do we get it? Oh, here's some corollaries. So so there will be a main result, and here are the formal 2 statements of the result. So so we can have the top one is a non-explicit graph. So there exists a graph in which the matching game can be evaluated efficiently. It's order log squared n, with just this repeating what I just said. And the bottom one is an explicit one. So the 4th criteria says that if we know n and k and the right node x, an index or I of the neighbor, then the ith neighbor is computed in time polylog n. So that's just repeating what I already explained in the previous slide. So, and we get it from a single result that is a Hull type theorem. So the theorem says that if a graph has good expansion, then there exists a polylog time matching algorithm from which we can get, then there exists polylog time matching algorithm, and then we apply it to existing constructions of expanders. So we need lossless expanders for this, and that's why the 2nd result is only optimal in quasi-polynomial of log n and not polynomial and log n. Okay, so let's go to the next slide. And let us explain what is Hull theorem. So here we see a graph, and we want to know whether it has offline matching up to 4. So any right subset of 4 nodes can be connected to 4 nodes at the left. So can we select 4 edges that are disjoint and cover the 4 nodes? And so to get this, we can apply Hull's theorem. So yeah, show it. Hull's theorem. Can you show the next slide? Yeah. So that says the following: like every right set with at most 4 elements has at least every right set S that contains at most 4 elements it has at least size of S neighbors. And so this property is true in the above graph. And how do we know it? So what is the above graph? So every so it has 5 nodes at the left and 10 nodes at the right, and 10 is equal to 5 choose 2. So every right node is connected to a different set of 2 left neighbors. Okay, and so of course every set of 1 element has at least 1 neighbor. Every set of 2 elements obviously has 2 neighbors, because every single node already has 2 neighbors. Now we can understand that every 3 nodes must have already 3 neighbors. Why? Because every 2 nodes go to a different pair of nodes. So already every set of 2 nodes has 3 neighbors. And now how can we understand that every set of 4 nodes must have 4 neighbors?
It's not clear, I guess. So if these 2 nodes do not share a neighbor, then it's clear. But it might be that they share, all of them can share a neighbor, right?
But only 3 times. So we have 4 nodes in the right. Yes. So 3 times 2, 2, 2. Yes. And the 4th one will give us 1 more neighbor. Yeah.
Yeah. So if we have 4 nodes at the right, they cannot go to 3 nodes, because in 3 nodes we only have 3 different pairs.
Right, right.
Yeah.
Right.
So now if we understand what is this graph, we can check the property directly with Hall's theorem. So it's toy example just to illustrate that it's very useful. Okay. And so now let us say our main result from which we get the corollaries that is important for applications. Okay, first to state the main result, I need to explain. Yes, you can go to the next slide. So Hall's theorem assumes 1 expansion, and we need a stronger assumption for our theorem to get dynamic matching. And so we need expansion close to the degree. So we need big expansion. And secondly, we will consider a modified version of a weaker version of matching game, where a left node can go to 2 different nodes. Okay, let us first start with formal definition. So a graph has E expansion up to K if every right set S with at most K elements has at least E size of S neighbors. So that should be clear. And so Hall's theorem says 1 expansion up to K is equivalent with offline matching up to K. And now let us present the next slide modified. First in the literature, what the literature says, that 3 expansion up to K means dynamic matching up to K. So it's old result from Feldman, Friedman, Pippenger in 1988. And again, these people were working on switching networks where expanders were introduced in early 70s, if I'm correct, at least in 70s. But it took till 88 until they made a connection with very important applications through this theorem. And so now, but there is a problem with this theorem, because the dynamic matching algorithm runs in time exponential in n. To be precise, it is n choose k, so up to polylog n. So that's very bad. And so they ask for a polynomial time algorithm. Can we relate expansion to dynamic matching with polynomial time matching strategy? And we did something better. We have polylog n time. So we need to improve their result to double exponentially.
But wait, your theorem also holds for every graph with 3 expansion.
So this, yes, their theorem holds. No, our theorem, we need a stronger assumption. We need expansion close to the degree.
I see. But
and
anyway, for every graph with that expansion, you have a fast algorithm.
Yeah. So we have oracle access to the graph, but we have a slightly weaker version of dynamic matching game. I will explain it soon, but it doesn't matter for application this beginning. So let us first discuss this result.
So,
of
Bruno,
FFP.
should I add here? So actually, this is a main open question in our paper, whether constant expansion is good enough for fast dynamic matching. And we suspect that it's not true, but we don't have a
Marius
hardness
thinks it's
result.
not true. Yeah, you think
Yeah,
this, but
I
I have
think
no
it's not
clue.
true.
Okay, let's go to the discussion of the. So what's their matching algorithm? Can you show next slide? Okay, so well, the strengthening, I don't know the answer whether we can get this theorem with 2 expansion. So then what is their algorithm? Next slide. So it's very easy. So each time you match a node, let's pretend that we delete this edge in the graph. So one of the players, so the matcher has a private copy of the graph, and each time he assigns a match, he deletes this edge from the graph. And then he will choose this edge such that the remaining graph has 1 expansion up to k. So that is his strategy. And then we need, so that's enough. We just need a lemma that there always exists such a neighbor, so that deleting the edge keeps 1 expansion up to k. And that's a special lemma. I mean, it would take half, it's 1 page in their paper, but written in cumbersome language and more general form. But even explaining it, probably 20 minutes. I will not do it because we don't need it. Okay, and what's the problem? So next slide. The problem is that checking whether a graph has 1 expansion up to k takes time exponential. It's co-NP complete problem. So in the input size, and the input size of this problem is a full graph. So the runtime is exponential in n. And there is no hope to, so that means that we need to go to a special case of this algorithm cannot be used, or maybe it can be used in some special case. Okay, so then let's go to our main result. And as I said, we need to a slightly weaker conclusion. We have dynamic matching up to k with a small amount of overlap. So next slide. So here we see a dynamic matching game with load L. And L means with load L means that we may reply, and the edges don't need to be disjoint, but a left node can lay on at most L edges. So opponent selects a right node, we can use an edge that has a certain left node, but the same left node can lay on at most L edges of the matching. And so why doesn't it, why we don't care about, so L will be small, L will be order log n in our algorithm, typically. And that means that if we have a graph with good expansion, then we can just take L copies of the graph, and then these L copies together have dynamic matching with load 1.
All right.
And so if L is order log n or quasi-poly log n, we don't care about this. Okay, so now we can get the main state in the next slide. So here is our main result. So if graph has right size n and degree d, and it has expansion 2/3 d plus 2, then it has dynamic matching up to k with logarithmic load. And we can evaluate the matching strategy in time order d times log n. So that's the main result. So again, compared to FFP result, we need more expansion and we need some load. Okay, what is next on the slide? Let's look. Okay. So there's under these two extra things, we get double exponentially smaller matching time. So what are the techniques that we are really using? So we will first I will present so there are two main algorithms that are somehow combined. First, two matching strategies that are combined. First one is a new strategy, and that's a poly n time dynamic matching strategy. So that's way too slow because we want poly log n time. But fortunately, we can combine. Fortunately, we just need this algorithm only a few times for a few matches. And the second algorithm is one that works in poly log n. Well, actually, log n, yeah. I should say order d log n, so the time that we need. And it's just a greedy strategy. And it's a strategy from old paper of Musatov, Romashenko, and Chen, but it also exists in some other places in the literature. And so then we will combine both algorithms. And if we do it in a trivial time, we get amortized time poly log n. And if we do it in a clever way, we get worst case poly log n time. So there are the 4 steps of the proof. So the hard.
I don't get it. If you have this new algorithm, why do you need anything else? Because this new algorithm already solves your problem.
No, we want matching in time order d log n, not poly n.
I see. Mm-hmm.
Yeah, so for applications and computer science, we really need poly log n, not poly n.
Mm-hmm.
Okay, but already the first step was difficult because people in FFP could not solve it. And I mean, it's from Princeton, they worked on, like Pippenger is Princeton and worked for a very long time on switching networks. And this connection with expanders, he wrote many papers about it. But
Bruno, I should add that poly n is still exponentially faster than Friedman and Feldman and Pippenger.
Yeah, that's what I said. So this is the FFP paper, and Pippenger was focused on connection between expanders and switching networks, and it means Hall's theorem. And I will explain this connection very soon. So don't worry, it's a very simple, nice connection. Okay. So next slide. Yeah, next slide. I mean, next overlay. Okay, so then this theorem, we can, so there exist explicit constructions of lossless expanders. Rate expense. Okay, I'm not going to explain the remark. Let's go to the next slide. Okay, so there are some open questions that we cannot answer. And so I said that we used 2 relaxations. Can we get the same result with load 1? So we cannot prove it, neither disprove it. And can we decrease the expansion from 2/3d plus 2 to O of 1?
But Bruno, wait, you have just explained that that making L copies, we can decrease the load to 1. So why do you ask this question then?
Well, it's just general. People want to know, if you have a graph, can you win the matching game? So dynamic matching has huge number of applications, but so there's like 50 papers a year at least that study dynamic matching, but it's slightly different model because there, when you assign a match, you can later reassign. So if you choose a neighbor, you can change your mind.
Mm-hmm.
But in our model, you cannot change. So we have to solve a harder problem.
Mhm.
But of course, one wants to have the best of both worlds. And so look to these people. So dynamic matching is for like web advertisement. That's the main reason. So you have people, you have messages of advertisement on one side, and then other side, people that look at looks to a site, and you want to map looks to advertisement somehow.
Mhm.
And so these people in advertisement, they study this a lot, but the advertisement can change on the website. Okay, and so of course we want to go better, and we want to look at fixed graph, and so we don't need load and copies, and even the statement of the theorem becomes better and easier to state, and more applications and so on. And okay, can we decrease expansion to O of 1? And can we do it simultaneously? We also don't know. And so Marius thinks, so we cannot get both simultaneously. I don't know if he has ideas about getting at least one of these improvements.
No, I don't. And actually, I suspect for the second one, it's a negative answer. But anyway, proving that should be conditional, because if P is equal to NP, then the algorithm from the Feldman, Friedman and Pippenger is actually working in polynomial time. So maybe under some hypothesis like the strong exponential time hierarchy, strong the SATH hypothesis. So maybe a condition of something like that, a harmless result can be shown.
So I rather think that it's possible to have both improved.
There are these kind of conditional results for the other kind of dynamic matching. So this is why it may be possible to prove conditional harmless
well,
results.
if I read this paper and this other type of matching, I think their results are incredibly powerful. And so I would suspect, so they're positive results, but I'm not a specialist in this. It's a huge number of papers, and I didn't have time to check it systematically. Maybe there is hope. Okay, but let's continue, and let's do some mathematics instead of definitions. So let's go to the next slide. Oh, sorry, I will explain the application, so more definitions, but then we go to the proof. So what is switching networks? So in old days, when phones were just invented, so there was a village with 5 people, and so they made phone lines, and they every pair of people was connected by a phone line, and that's how they worked. But then when more people got phones, it was no longer possible to make a connection between every pair. And so they introduced special nodes which they called switching station. And so the plan was, if you want to call to someone, you first call one or more switching stations, and they make a connecting line for you. And so the question is, can you connect, given a bunch of disjoint pairs of people that want to connect, can you make a network so that all of them are connected? But all the lines need to carry, so one line cannot carry 2 people. So initially, it's like switching stations, they were connected by edges, and every edge could carry 1 line. And so that is the history of switching networks. And now for phones, it's not needed anymore. Computer can do whatever, fiber optics and so on, but it still happens inside the computer. There is a huge number of memory blocks and now a huge number of processors, and they need to be connected very fast, and they do it also through a switching network. And they say that there are much more more things like this. So they place satellites around the Earth, and they have to talk to each other with limited capacity. There is a connection with multi-commodity flow problem. That's a huge number of papers. And okay, but here we are choosing the graph. But what we have now is that inputs and outputs are different in current applications, and we deal with bipartite graphs as in the paper here. And there are two aims. We want to minimize number of edges. Number of edges is proportional to the price. Okay, also number of nodes play a role, but let's simplify things and just minimize edges like is done in most papers. And we want a fast path finding algorithm. That means if a request of input-output pair appears, can we build the graph very fast? Okay, next slide. And so here is the, so let's go to the definitions. An N network. So I will use equal number of inputs and outputs. N network is directed a cyclic graph with N output nodes and N input nodes. Okay, and then what is a rearrangeable network? That's the definition at the bottom. That's a network in which every permutation can be realized. And what does it mean to be realized? It means that we can give, for every permutation, we can point at N vertex disjoint paths. So N vertex disjoint path, of course, connecting an output to its input. So in the top, you see a rearrangeable N network. So you can check for yourself that every permutation you can implement.
But wait a bit. Here the number of inputs coincides with the number of outputs, right?
Yeah. So I consider a special case for simplicity.
And the only way, the only thing we need to know that for every permutation, how it's related to the dynamic matching. It's
next slide, I will explain this.
Okay.
First, I want to make sure you understand, in 2 slides, because we will use dynamic generalization of this. Okay, so rearrangeable network. And let us say something easy first. What's the minimal number of edges in a rearrangeable N network? So for this, so the bottom is that the minimal number of matches is log N factorial. And so can you tell me why the lower bound is log N factorial?
Probably because there are N factorial one-to-one mappings.
Exactly.
But why do we take the logarithm? It's not clear.
For number of edges.
Maybe somehow we realize each such mappings by choosing some number of edges, and so the number of ways to choose edges is 2 to the number of edges, and it should be at least the number of mappings, right?
Yeah, exactly.
Uh-huh.
So for every permutation, we need we need N disjoint paths, and they are a subset of edges.
Mm-hmm.
And so we have N factorial permutations. So we need N factorial subsets of edges, different subsets. Okay, so that gets N log N lower bound. Okay, and so next slide. Here we will focus on
one question. I'm sorry. Sorry.
No.
Right.
Yeah.
The N network here is not rearrangeable, or is it rearrangeable?
It's rearrangeable.
But how to realize the identity permutation? I mean, this node to this node and the second to the second.
Oh, wait.
I see a little
Yeah.
problem, or maybe I'm not right.
No, you're right. You cannot
Okay, thank you.
realize identity like
Just to realize that
one,
maybe I
to
don't understand something. Yeah.
Okay, sorry, I'm completely wrong. Yes, I overlooked it.
Okay, thank you, great.
Yeah. And actually, first constructions of rearrangeable networks, like until end of 80s, followed construction of certain networks. And so the best construction used AKS sorting until some, yeah, the next slide shows the paper. So can you show next slide? Oh, sorry, too early. So we need a dynamic variant of this. It means that opponent can give input-output pairs. And then he can also discard input-output pairs. And then the path is also discarded. But once an input-output pair is assigned, it cannot be changed anymore. So that's the dynamic variant of the problem. So they, in the literature, there are two dynamic variants called wide sense non-blocking and strict sense non-blocking. And so they're very closely related, but different. And we use the weaker one of the two that corresponds to a similar game as the matching game. And there is another generalization. So we don't need to have a permutation, but any function from outputs to inputs. So an input can broadcast to multiple outputs. So you can think about people. So you can broadcast movies to many people. And so it's an application used in broadcasting networks. Okay, so this is called generalized network, the connector. Okay, and so we have this game. Yes, and now next slide. And so Aurora, Layton, and Max, they created such a network, dynamic network. And before their paper, all such networks were based on AKS sorting, or the best networks. But they made an explicit simple construction with fast pathfinding algorithm, and everything looked really nice, but engineers were still not happy. And so that there followed more research on this thing. Okay, so it has long history that started in the 50s with Claude Shannon, who proved the lower bound I just explained of n log n, and then they wanted to have explicit constructions that matches this bound and so on. Okay, but we on next slide we will focus on networks with constant depth, because when you sometimes making a connection between two nodes is slow, and people want to have fast connections. And so next depth is maximal length. Yes, next slide. And so there is a history of this result. There are quite some papers, but it's incredibly hard to get the history, because a lot of applications exist, and these engineering people, they have always slightly different constraints or some extra things they can use. But Pippenger has many papers. So PY is Pippenger and somebody else got a lower bound. Then FFP is a paper we discussed. So any network with depth D needs to have at least n to the power 1 plus 1 over t edges. And so non-explicit constructions, you can get this upper bound. But the pathfinding algorithm is exponential in n. Then Wigderson and Zuckerman gave explicit constructions that match the upper bound up to quasi-poly log n should be. I wrote quasi-poly n, that should be log n edges.
Yes. PY is Pippenger and Yao.
Yeah, but their pathfinding algorithm runs the dynamic matching algorithm from FFP. And so their pathfinding algorithm is also exponentially slow. And then there are people, many papers with faster pathfinding algorithms, but the number of edges is not optimal. So it is 1 plus c over t for some c a little bit bigger than 1, but some constant c. So they have a ridiculous number, 24 divided by 23, for example, such weird numbers. And so in practice, it's very good because all engineers, they complain. So there is a book of Ha-Wang, and in the introduction, he says that he will only speak in 2 chapters about mathematical constructions and then switch to engineering because they all have big O constants, and it destroys whatever gain is in this C that is bigger than 1. So that's why engineers lost some interest. But in theoretical computer science, there are many papers about extractors, expanders, and unique neighbor properties, but they keep citing these network properties, although the engineers are unhappy about it. Okay, and so in this work, we get, so this work adds to the maybe useless research for engineers, because we give non-explicit construction with optimal number of edges and reasonable pathfinding. So there is a non-explicit and explicit variant. Okay, yes, and now how do we get these applications from dynamic matching? That was already asked. It's in the next slide. Okay, and I make a drawing. I start. So the construction is very easy. So here we have a huge. So let us draw a huge graph at the right and a smaller graph. So I will say depth. Let us make the construction for that tree network. We want to have and let us look to a graph with dynamic matching. So here we have a graph with dynamic matching. So here we have n right nodes. And let us have here n to the power 2/3 left nodes and a graph with dynamic matching here. Now let us have a recursive constructions for that 2 here. Which is here we have an n 2/3 connector.
So Bruno, n is the number of right nodes in the switching network, right?
Yeah. And so now I explain the connection.
Mm-hmm.
So imagine the construction is recursive in n. Recursive in the depth. And so we copy, we have n to the power 1, 3 such connectors. So that's our plan. Okay, I'm approximating something. The numbers are slightly off, but this doesn't, let's ignore this. And so that's the construction. So what's happening here? So this is a graph with dynamic matching. So what does it mean? By the way, I forgot to tell, for one depth connector, we take a fully bipartite graph. So here we have all connections. And so here we get depth 3. And here we have recursive applications. So this is not all connections. So here we do the same thing. We look to blocks.
So wait a bit, you have n to the 1/3 blocks, and in each block, what is the number of nodes in the left?
N to the power 2/3.
Again.
Yeah. And then here we will have here we will make here we will, in each block here we have n to the power 2/3 at the right and n to the power 1/3 here. And again we have inside each block, so we do it recursively. Here we have n to the power 1/3 blocks, like mini blocks. And here we have fully connected.
And
And
in
so,
the right half of these, what is the connection in the second, in the right half of one block?
yeah, so we have in the right half. So on the right, each graph has n to the power 2/3. On the left, n to the power 1/3. And then the fully connected has n to the power 1/3 here and n to the power 1/3 here. And so we see that every right node. So imagine that in the graph, so in the matching graph. So we use two different graphs with matching. So we use n to the power, so matching with right node n and k equal n to the power 2/3. And then the 2 times we use n to the power 2/3 to k equal to the power 1/3. And so if every node in this graph has degree d, and d is polynomial in log n or quasi-poly in log n, then the degree of every node here is d times n to the power 1/3. And so for every block that we create, we get d to the power n to the power 1/3. And so what do we have here? So let us ignore the output nodes. Then all the other nodes, they have degree d to the power n 1/3. So number of nodes is equal to d times, every column has n nodes, and then d times n to the power 1/3, this number of edges. So that's how we get, so this equal to n to the power 4/3, or n to the power 1 plus 1 over 1/3, and t is that. So that's how we connect matching two connectors with optimal construction. And so pathfinding, I forgot to tell, but do you understand it? So if we are given an input node here, and we need to connect, for example, to a node here. So what is the pathfinding algorithm doing? So it will look to this graph, where the left nodes are these graphs, and it will ask for a match here. So it will connect to some node here. So it will select, and then we do the same here. We look to the dynamic matching algorithm. Sorry, we need to go here. So I ask for this node. So we need to go here. And so we ask to this graph for a match to one of the nodes here. And so it will give a second match. And then we have a fully connected graph. So we can go from here to the final node.
So why do we need dynamic matching here? Can you explain this?
Okay, I explain again. So how is the pathfinding algorithm works? We receive a node here, and then we want to go here. So we identify the n 2/3 connector where it works. And then we look to the dynamic matching graph that goes to this connector, and we ask for a match. And so we get a match.
But at which time edges will be removed? I don't understand. So the dynamic matching means that
Yeah, I just can be
sometimes
removed. Well, in this connection game, we get also that pairs are removed. If the pair is removed,
I
then
see.
all these graphs have to remove their match.
I see. Mhm.
And so it's very simple construction.
Mhm.
So if we have dynamic matching, we can make this graph with efficient routing. And but literature on routing algorithms is huge. I was reading the last 2 days about it. Okay, so now the connection is clear. And so can you tell me about time? What is it? 7:15. So there is not much time left. Well, I need to present the results. So can you go to the next slide? Okay. So now it is the proof. And so let me do one little proof just for the greedy algorithm. So let us recall the dynamic matching game. And I already explained that when we have some load, we will take L copies. And so I will prove the greedy algorithm, not with load, but with copies of the graph. Okay, so let us recall the game. So adversary removes edges from M. And afterwards, there are at most k minus 1 edges, and he selects a right node, and we need to add an edge that does not touch the other edges. Okay, so let us go, let us present the greedy algorithm. Let us first present, next slide, the result. So let us first consider a special, so before I prove the result for the greedy algorithm, let's use an easier result. Let's consider the matching game that in which the opponent does not remove edges. So it's called incremental matching. And some time ago, we called it online matching. But now online matching is used for dynamic matching. So we need to name incremental matching. Okay, so if a graph, the claim is if a graph has a 1 expansion up to k, then a 2 plus log k clone wins incremental matching up to 2k. So in this game, opponent selects right nodes, and we need to choose a left edge. And our strategy will be very easy. So, so what is a clone? That's just a clone of a graph is an L clone of a graph is obtained by taking L copies of the graph and identifying the right nodes. Okay. Yes. And so if in an L clone, in a 2 plus log k clone, we can win the incremental matching game up to 2k elements, provided it has 1 expansion up to k. That's the lemma. And so the strategy, okay. So now we want to prove this lemma. Oh, no, sorry, just keep it. Then I will prove the next lemma, and then I will go to the second application, and then the seminar is finished. Okay. So the proof will go by induction on K. So what I say that if the theorem is proven for matching up to K, so assume proven up to K. So assume it works in the matching game up to K. And then we want to say that one more copy, we can get 2K. Okay. So I will prove by induction. The base case is easy. If K is equal to 1, then we have one dynamic matching up to 2 using a 2 clone. So in the 2 clone, every node has 2 neighbors, so we can match any 2 nodes. Okay, so now assume that with an L clone, we have matching up to K. Now with L plus 1 clone, we get matching up to 2K. So let us prove it, and it's actually not so difficult. So let us make a graph. And so let us look at first copy. So first copy of the graph. So there are edges here. And let us also look at other copies. So here are other copies. And I will prove that at any moment with the greedy algorithm. So it selects the first clone that has a free neighbor. So here is the first copy. So we choose the first copy and the clone that has a free neighbor of a node. So I prove that at any moment, the number of matches assigned in the first copy is at least the number of matches assigned in the other copies. And so Kolya already has learned why this is true. So let us look at the nodes that do not have a match in the first copy. So the matching algorithm receives nodes and it has to choose a neighbor here. So let us point at all the nodes that are not assigned in the first copy. We know that all the neighbors of these nodes are not free by the match, because if it had a free neighbor in the first copy, it would be matched in the first copy. And so now we can conclude that the number of nodes matched in other copies is at most number of nodes matched in the first copy. So do you see why? We didn't use one expansion, so it follows by one expansion. So can you see why? So let S be the nodes that are not matched in the first copy. We know that all their neighbors, let's look at the set of all their neighbors. So imagine that all these neighbors are matched of each such node. And so we get...
It has more nodes than S.
Yeah.
And that's that means that S is at less than K.
Yeah. So if we have K
than
rejected nodes here,
uh-huh.
K nodes that are not matched in the first copy, then the neighbors of these K nodes are nodes that were matched in the first copy. So the set of all neighbors of this node is at least K. So here we have neighbors of S is at least K by one expansion. And all these neighbors, they have a match in the first copy. So the moment that we reject K nodes, we must already have assigned at least K nodes in the first copy. So conclusion, number of matches assigned in the first copy is at least number of matches assigned in the other copies. And that gives us inductive proof of inductive statement. So in every clone, the number of matches decreases at least geometrically. And that's how we get the log K. Every next copy has at least half of the matches of previous copy. Okay, so if it's not clear, then I should repeat that.
No, I guess it's clear.
Yeah, it's for you because you learned this long time ago.
All right.
But for the others, it's new. Because it's from Ramashenko Shen Musatov paper. It's from 2011. So they invented this string. Okay, let us clear everything and go to the next slide where we extend this result. So now, what if we don't have K rounds, but we have T rounds? T is bigger than K. Then in such a game, the greedy strategy works with a minor modification. And what is this modification? So when opponent wants to retract, we will wait a bit because maybe he might change his mind a bit later. And so we just pretend we didn't hear the retraction and we wait until the next round T, which is 0 modulo 2k. So we wait every 2k steps. And then we process all retractions. It looks like a stupid strategy. Why postpone retractions? It makes the work harder for us. But it turns out that if we postpone, then we can prove something. So, and then otherwise we continue to play this greedy strategy. And so the question is, why does this work? And so again, it will go by induct, yeah.
And then we violate the rule because assume that the opponent retracts an edge, and then he asks for a match for its right end, right?
Yeah.
And what? Probably we take the retracted edge. Just take the retracted edge.
Yeah,
then.
yeah.
I see.
Yeah.
Mm-hmm.
Okay, and so we have a little bit weaker. Previously we had 2k here, now we only have k, but it also works for t larger. And so again, this will be proven by induction. And so for t equal to k, it's already the base case. That's the base case, it's previous lemma.
Bruno, excuse me, you have only a couple of minutes left. Maybe we need to
Okay, yeah.
see other applications. It's more interesting.
Yeah, okay. About 1-bit probes. Yes. So let's go to, I clear everything, go to the next slide. Just continue to the next section. There is 3 slides or something. Okay, so now let's speak about 1-bit query probes. Okay, so there is a result about dynamic matching where we match to a right node to most of its left neighbors, and we get a variant of this, and this was used to prove theorem about fast compression algorithms at the price of slow decompression. So any string can be compressed to its Kolmogorov complexity in polynomial time. But we need to know a target length. So we need to know the value of Kolmogorov complexity. Okay, and this same theorem can be used to prove something about bit probe. So it should have been in the same paper, but I didn't know about this application. Okay, so let us now go to bit probes. What does it mean? It's a data, next slide, a data structure to store a set. So here is the problem. Given a set, which belongs to integer numbers of at most n, and a subset of size at most k. And we want to store s in smallest amount of space to answer queries is x and s. And we also want to know very fast whether x is in s. So next, so there are 2 ways. So we will look to the query complexity as how many bits do we need to read from data structure. If we store s as n-bit vector, and so the x bit is equal to 1 if and only if x is in s. So then we have a large, so typically k is much smaller than n, and in this case this is there's a lot of memory needed. But we can get the result, the answer we can get by reading 1 bit. And now we can go to the other extreme. We can read a lot if we choose S as a sorted list. Then we can get optimal size, k log n. There is no way to store a set more efficiently unless some special values for k. So in the case that k is much smaller than n, you cannot do much better. But the problem is that if you want to know whether x is in S, you have to do binary search on the sorted list. And so you use memory order k log. Bits per query is log k times log n. So mistake on the slide. Okay, next. And it turns out we can combine both features. So we can make a data structure that reads just one bit and has size close to k log n. And that's called, so a one bit query probe is a data structure for that reads just one bit when you make a query and gives the answer with high probability. We will use probability query answers. And it's not the same as Bloom filter because here in our data structure, for each input, the answer should be correct with high probability. So in Bloom filter, Bloom filter stores not the exact set, but a superset. And then with some probability over the construction of the superset, the answer is correct for each x. But here it's different. Here we want to store the exact set S, and when we make many queries, we should be correct on average. So if we try all the random seeds, we should have the correct answer. Okay, and so the aim is to minimize the size of this data structure, the bit size. How many bits do we have? Next slide. And here are our results. Okay, next slide. Next. Okay, that's the history. So it was introduced in very famous book about perceptrons from Minsky and Paper. They started to study this. Then it was picked up after some time by Burman, Vatan, Venkat. Okay, I forgot the names of these people, and they give non-explicit constructions using expanders. And this non-explicit construction was optimal up to factor order 1 over epsilon squared. And epsilon squared, epsilon is the error probability when you make a query. And they have explicit construction with size k squared. And then people try to decrease the size. So there is Tajma who decreased it to k up to quasi-poly log n. And then Guruswamy Uman Vatans got even a little bit better for small values of k. And so we managed to improve the sizes of all these constructions if epsilon is at least, yeah, next slide. Next. Yeah, and so here in the bottom, you see our result. So we get the size k times 2 to the power order. So we have better size provided epsilon is at least k to the power minus big O of log k. So that means unless epsilon is extremely small, our size is the best with an asymptotic notation.
But Bruno, it's more, so the previous skills didn't allow for insert and delete.
Yeah, I still explaining. Okay, and our construction has extra feature because
and it's still one bit query.
Yeah,
right?
1 bit query.
I see.
And our construction has a second good feature, because previous construction, you cannot insert or delete an element. If you change the set at start, you need to recompute everything, and it takes time, k polylog n. But in our construction, we can modify the set, and each change, adding or deleting an element, takes time k quasi-polylog n over epsilon. So it's improvement, so both from static to dynamic and on the bit size. And the change was something very simple from a polynomial time compression paper. So it's very, very small change. So there, so adding an element. So adding, sorry, somebody comes. Okay. It's like today, every technical thing is going against me. Okay. Yes. And so I said that there's just only one very small change that we had to do from fast compression paper. Fast compression paper is basically a matching algorithm. So on the right, we have strings. On the left, we have programs. And it's a rich matching because we can match every write string to most of its neighbors. So the compression is just randomly selecting a neighbor. And here we do something similar. So when we assign, when we add a node to the set, we set all the left neighbors that are selected by matching algorithm. We set their bit to 1. And so the left neighbors tell us whether the element is in the set or not. And so if we have rich matching up to k plus 1, then we can store k elements in the set structure. And so why do we need rich matching up to k plus 1? It is so all the elements in the set have their left set bits to 1. And then we pretend that, so now we have, so it's obvious that if an element is in the set, then the query answers correctly. Because if we select a random element, then with probability 1 minus epsilon, we hit a selected left neighbor and its bit is set to 1. So that's clear. But then, we need to prove that if an element is not in the set, then it is only epsilon fraction of its neighbor has bit equal to 1. And to do this, we just pretend that we give this element that's not in the set, we give it to the matching algorithm. And then it will select 1 minus epsilon fraction of its neighbors and set it to 1. But these neighbors have not been selected by other elements because edges need to be disjoint. And so that means that their bits is set to 0. And that's like the idea. And so that's the connection. From matching, we go directly to 1-bit probes. And it's a connection that was missed in Goof paper. But of course, you first need to have this rich matching algorithm. And so they used another thing with error correcting codes that's very complicated and then eventually gives non-optimal size for most values of epsilon. Okay, and that's the end of the talk. Let's double check on the next slide.
No more slides. Thank you, Bruno. Are there any questions, comments, or something to Bruno?
No. I guess not.
Okay, there were a lot of questions during the talk, so I hope now it's absolutely clear. Thank you very much again.
Yeah, Bruno. Yeah, it was very interesting.
Okay, thank you.
So thank you. That's all for today.
Yeah.
Nice evening.
See you
Thank
next time.
you.
Thank
Thank
you.
you.
Bye.
Bye.